This is the Theory and Calculations lab lecture video for the titration of sodium hydroxide and KHP potassium hydrogen phthalate. So first, let's talk about the background of the titration, which is a type of procedure. It's a skill that we learn. So with titrations, they can be done for pretty much any type of chemical reaction you can think of. This one is specific for an acid-base reaction because we have a weak acid, KHP, that H is able to be donated, which is the Bronsted-Lowry definition of an acid, and then sodium hydroxide, which is one of the 8 strong bases. So they're going to react as an acid and base will, but any titration, we can do a titration for any chemical reaction. So the purpose of a titration is to accurately learn the concentration or the amount of a chemical in the chemical reaction. So we use indicators, which are chemicals that are not part of the chemical reaction, but change color at an important time. And that important time is at the equivalence point, which is when stoichiometrically the moles of both reactants are equal. Now, technically the indicator doesn't change color until immediately after the equivalence point, and so that color change happens at what we call the end point, which is when the titration ends. The equivalence point is when we'd like it to end, but because of the way indicators work, the color change doesn't happen until we've added 1 drop extra of the reactant that is in the burette. Okay, which is why when we're doing titrations, we're always aiming for whatever the color change is. We want immediately when that color change happens. So for this lab, the color change was going from colorless to pink. So we wanted to stop at the lightest pink color possible because technically any pink color is past the end or the equivalence point. So we want to be as close to the equivalence point as possible, which means the lightest color we can possibly get. Okay, so when we're doing our titration, we need to accurately know information about one of the 2 reactants. It could be that we accurately know the chemical that we put in the Erlenmeyer flask at the bottom. So like in part A for this lab, you accurately measured out the mass of KHP solid. And so that was accurately known. And then you were trying to determine the molarity of the sodium hydroxide, the solution that's in the burette. It can go the other direction, like in part B, when you will have accurately determined the molarity of the sodium hydroxide. And then using that same molarity, you're going to test an unknown. That unknown contains some amount of KHP and some amount of other crap. Most of the other crap is sodium chloride, which is not an acid or base, doesn't react, but it's just taken up space in the mass. So when we do a titration, often, just like this one, the first part is called the standardization. So standardization, or standardizing, is accurately determining the molarity of the solution in the burette. And when I used to work in industry where I was testing pharmaceutical drugs, I'd start my day actually calibrating all of the balances, making sure they were level, putting little masses that we accurately know their mass on there, making sure that it works out, calibrating the pH meters, which you guys will learn how to do here in a little bit. And then I would make solutions as I needed for the day, and then standardize the solutions that I needed to know accurately. Okay, so for this lab, again, the chemical reaction that we're doing is between sodium hydroxide, so NaOH, and potassium hydrogen phthalate, which I'm going to write the whole thing out, and then I'm going to write underneath it or above it the abbreviation that we're going to use for because it's long. Phthalate is a polyatomic ion, so it's not like it's difficult. It's just not a polyatomic ion you're used to dealing with. So when this happens, the hydrogen from the KHP is donated to the hydroxide, which becomes HOH, which is H2O. And then the sodium is picked up by the potassium and the phthalate polyatomic ion. So this is, we're going to abbreviate, and the procedure calls it KHP. P is the first letter of the name of this polyatomic ion, phthalate. I know it sounds like a T, but PH is. Okay, so that's the abbreviation for that. So in part A, our goal is to figure out the molarity of the sodium hydroxide. Now, the lab does tell us it's somewhere around 0.1, okay? But that's not accurate. That's just an estimate, okay? So, I'm going to give us a pretend scenario. So some pretend data. for an example of part A. So pretend like I did my titration, and our data would be, we'd have milliliters of sodium hydroxide, because you're going to have your initial volume and your final volume, and you'll subtract those to get how many milliliters of sodium hydroxide you had to add before the color change happened and you reached the end point. You will also accurately know the mass of KHP that you measured out. Now, your numbers are not going to look like my numbers, okay? Your KHP is going to be between 0.4 and 0.6, which is going to mean your sodium hydroxide is going to be lower, okay? So the end goal of this is to know the moles of sodium hydroxide divided by the liters of the sodium hydroxide. Well, we have absolutely no information about the moles of sodium hydroxide, but we do know the milliliters of sodium hydroxide, which we can easily turn into liters. So we kind of know what that 41.35 milliliters is going to be used for later. We need to find the moles of NaOH, and then we'll be able to divide that by the 41.35 milliliters once it's converted to liters. But again, I have no information about moles, so I'm going to have to use the grams of KHP to start my calculation, and we're going to be using that number to get ourselves to moles of NaOH. So first I'm going to use the molar mass of KHP, 204.22. That's how many grams there are in 1 mole of KHP. Because again, KHP is not a potassium, a hydrogen, a phosphorus. It's a potassium, a hydrogen, 8 carbons, 4 hydrogens, 4 oxygens. So that's where the 204.22 comes from. So I'm canceling that out. It's awesome. But I need to compare moles of KHP to moles of NaOH. This is stoichiometry. It's things we learned in Gen Chem 1. Okay, so looking at the balanced equation, KHP has a coefficient of 1, so there's a 1 right there. Sodium hydroxide has a coefficient of 1, so there's a 1 right there. So I can cancel out moles of KHP. So if I stopped right now, my answer would be in moles of sodium hydroxide, which is wonderful. But what I want is the molarity, which is moles divided by liters. So I'm going to take my volume, 41.35 milliliters. And it's not in liters yet, so I know I've got to do that math. So I'm going to use the 1,000 milliliters to 1 liter thing. Cancel out the unit milliliters. If we look at the units we have left, we have moles of NaOH on top, liters on the bottom. So I'm going to grab my calculator. 1.1220 divided by 41.35 divided by 204.22 times 1,000. I ignored the ones. Okay, so looks like I've got 4 significant figures because my mass had 5, my volume had 4. So I get a 0.1329 when I round it to 4 sig figs, and then my unit would be molarity of NaOH. So you're going to be doing this calculation for each of your 3 trials to solve for the molarity of sodium hydroxide based on your data in trial 1 and trial 2 and trial 3. Now, it's the same sodium hydroxide the whole time. You used the same container of sodium hydroxide. So hopefully those 3 molarities are close together because you're measuring the same thing just 3 different times. So we're going to be measuring the average and then the standard deviation, which standard deviation is a measure of precision, which is consistency. So I'm going to abbreviate it by lowercase letter s. And here's what the standard deviation equation looks like. And I'll explain all the letters here in a second. Now, the square root is over everything. Okay, so the x with the line is the average or the mean. Those words mean the same thing. x1, x2, x3, those are the values from the trials. Trial 1, trial 2, trial 3. N is the number of trials, like your number of data points. Well, you have no choice. For this lab, you have to have 3 trials because the lab tells you that. Okay, so following this, we're going to subtract trial 1 minus the average and then square that number. And then trial 2 minus the average and square that number. And trial 3 minus the average and square that number. Add the 3 values together, divide by 3 minus 1, which is 2, and then take the square root. We're hoping this number is going to be very, very small. Okay, so let's say in my pretend world, this was the number that came out of my calculator for the standard deviation. Okay. Now, this is a calculated value based on data values. So we do have to apply significant figures to it. So the way you're going to handle significant figures, I'm going to use my average. Let's say my average was the average that I calculated on the previous example. Now, you're doing some subtraction, some addition, some division, and then square rooting, which we're going to consider square rooting kind of like multiplication. And basically, we're going to ignore the square root thing in squaring. But we're doing subtraction and division. Well, when we do our division, It's going to be the numerator divided by 2, and that 2 is an exact number. So really, sig fig wise, the important math that we're doing is the addition and subtraction. Okay, so with addition and subtraction, we're looking at the number of decimal places. So here's a way to kind of cut through all of that and help you figure out what's going on. You need to look at your average number. You've already went ahead and put it in the correct number of sig figs, like we did on the last one. Look at the number of decimal places it has. So 1, 2, 3, 4. It goes 4 places past the decimal point, so 4 decimal places. That means your standard deviation will also have 4 decimal places because we're adding and subtracting with this number, and it's all about decimal places. So 1, 2, 3, 4, 0.0018 will be my standard deviation rounded correctly. Okay. There's not a line for unrounded and rounded. There's just a line for rounded. So like it doesn't say unrounded with the standard deviation, so go ahead and round it with the correct number of sig figs. And then after that, we have to calculate the percent relative standard deviation, RSD. Okay. This calculation is taking the standard deviation divided by the average and then multiplying it by 100. So standard deviations measure precision, which is how consistent you are. So that's why we want the standard deviation to be very small, which means there's not very much deviation between your 3 measurements. Okay, the smaller the standard deviation, the closer together your values are. But 0.0018 looks really small to me. But so does like 0.095. I mean, I don't know what's small and what's not. Like, what's a good standard deviation? You can't really tell just by eyeballing it. What we need to compare is how big our difference is compared to the values that we're measuring. So once we do our standard deviation, we've calculated it. The percent relative standard deviation lets us know how good our value is. So I'm going to follow the formula. Take 0.0018 divided by the average, 0.1395 times 100. And so what we're hoping for here is a small percent. And you're going to be graded on your precision based on your value of the relative standard deviation. So when I did this, I got 1.3%. So for this titration lab, I'll tell you the scale on how I'm grading you based on your precision. If your percent relative standard deviation is between 0 and 1%, 1 to 2%, 2 to 3%, 3 to 4%. I'm going to not continue all of the points. If it's 0 and 1%, you get full credit. If it's 1 to 2%, you're going to miss 1 point. 2 to 3 minus 2 points. 3 to 4 minus 3 points. Now, when I grade your lab reports, they're out of a certain number of points from the syllabus. But when I grade it, it's not out of that number of points. So this is like instead of 1 point, think of it kind of like 0.1% is closer to what the 1 point would be. So you're aiming for a small, hopefully between 0 and 1% relative standard deviation. As we go further and do later titrations, your ranges are going to shrink. It's going to get down to between 0 and 0.5 relative standard deviation to get full credit, 0.5 to 1 minus 1, 1 to 1.5 minus 2, etc. But you can see this is what's happening for right now. Okay, so let's look at part B. We haven't talked about the part B calculations. In part B, you redid the titration, so it's the same reaction, NaOH. I'm going to be super lazy now, and I'm going to write KHP instead of the entire polyatomic ion. We're still going to make water, and we're still going to have potassium, sodium, and the phthalate polyatomic ion. Now, what's different in part B? You're going to have data values. I'm going to go with 18.20 milliliters of sodium hydroxide. You'll have some value. You're also going to have some mass of unknown, 0.5502 grams of unknown. Now I'm writing that under KHP, but that is not grams of KHP. That is grams of unknown. I wrote it under KHP because the unknown has some KHP in it. Okay. Now, you're also going to know, after doing your calculations in part A, what the molarity of sodium hydroxide is. You're going to use your average molarity of sodium hydroxide. Okay, so I guess I'll use the number from before, although that's not the number I used in my example. So hopefully this works out. So you'll know milliliters of NaOH, molarity of NaOH, which I guess I should write. It's your average value from part A, which means yours will be different from the other people in class. Hopefully they're still sort of similar because you're all using the same sodium hydroxide, but you will not use the number 0.1395. That's my pretend number. You're not using any of these values. These are just pretend values, okay? We know how many grams of unknown. So our first job is to figure out how many grams of pure KHP there actually was, and then we're going to be going for the percent of KHP in the unknown. Those are our calculations that we're solving for in part B. So first we got to start with to solve for grams of KHP. So I'm going to write that down. I want to solve for grams of KHP. The grams of unknown don't help me at all because it is unknown. You can't use that number to calculate anything about KHP because it's an unknown, which means you know nothing about it, okay? So we need to use our values about NaOH to do our calculation. We never start a calculation with a molarity. So I'm going to start with 18.20 milliliters of NaOH. Now, I'm going to convert milliliters to liters. And then I'm going to use my molarity as a unit vector. Molarity is moles per liter. So that means there's 0.1395 moles of NaOH in 1 liter of NaOH because it's just a complex unit. Now that's great and everything. That's moles of NaOH, but I don't care about NaOH in this problem. I care about KHP. So now it's time to use the mole ratio from the balanced chemical equation. Sodium hydroxide has a coefficient of 1. KHP has a coefficient of 1. So that's where that came from. And then I now need to go from moles to grams. So I'm going to use the 204.22 molar mass of KHP, which is the same molar mass I used in the last example because it's still KHP. So when I do this, 18.2 divided by 1,000, or 18.20 divided by 1,000 times 0.1395 times 204.22. Again, I just ignored the ones. It looks like I'm going to have 4 significant figures, so 0.5185 grams of KHP. Check. I just figured out grams of KHP. Now we'll have to do this for each trial. For each trial, your volume number is going to change, but your molarity number will not because you're always going to be using the average value from part A. And the 204.22 will not change either because the molar mass of KHP doesn't change. Now once you know how many grams of KHP there are, to know the percent of KHP in the unknown, all we're doing is comparing the grams that we calculated of KHP to how many grams of unknown. So what this is saying is, based on my numbers, there was 0.185 grams of KHP in my sample. Now, that wasn't my whole sample. My whole sample was 0.5502. So I'm going to see, well, then what percentage of the unknown is the KHP by doing just a, like I said, it's a percentage calculation. I guess I'll kind of block it off. And we do have to use significant figures when we're doing percentages. So 4 sig figs here. So 94.24%. Now, your values for the percent KHP are going to vary. Everybody's going to have their own unknown number, and that unknown number is going to have its own percentage of KHP. But they're normally going to be more in the world of like 25 to 75. This is a pretty high percent KHP. For the unknowns that we own, but it definitely will not be less than 10%, and it will not be this close. It will not be between 90 and 100. But based on my data, this is what I got. So you will then calculate the average of the percent KHP, the standard deviation of the percent KHP, and the relative standard deviation for the percent KHP, using the standard deviation and the relative standard deviation calculations that we discussed earlier. When you're doing standard deviation and relative standard deviation for percentages, like this number, its unit is percent, it doesn't matter what its unit is, just do the math. So don't take 94.24% and make it 0.9424. That screws up all the math. Leave it the way it is. If your average was 33.60, then when you do your standard deviation calculation, use 33.60 as the average. Okay, don't convert it to decimal form. Let me know if you have questions about this, but most of this math is actually not so much Gen Chem 2 math, it's Gen Chem 1 math.